Hey, what is up? It is April 13th, 2022. Welcome to Coding with Chef. Yeah, so let's get into it. I skipped yesterday because I had a bunch of stuff going on, and a lot of work related stuff, and also I got up later than I wanted to, so kind of intersected into the work day, the coding stuff that I did or that I wanted to do. So yeah, my daily algo cycle was messed up. Hate when that happens. So today was similar because I had to get up early and do some stuff. But I have decided to go full force, whole hog today, and get algo problem in. And I have a nice one for you, for those of you who have not seen these kinds before. This is called the Game of Life, and it's not the Game of Life, the board game, which you've seen all as a kid if you were growing up in the 80s, or maybe now. I don't know how it is now, but the Game of Life is a famous computer science problem posed by a mathematician, John Conway, who unfortunately he passed away in 2020. He was like 90 something, I think, but he had developed this problem in 1970, so about 50 years earlier. I guess, yeah, when he was in his 40s already, or something. Anyway, so and this is a really interesting problem because this is a problem that is it kind of demonstrates emergent behavior, and we're going to solve a simple version of it, a one state transition version of it. And yeah, so here we go. So according to Wiki's article, Game of Life is also known as simply as Life, is a cellular automaton devised by the British mathematician John Horton Conway in 1970. The board is made up of an M by N grid of cells where each cell has an initial state, live, represented by a 1, or dead, represented by a 0. Each cell interacts with its 8 neighbors, horizontal, vertical, diagonal, using the following 4 rules taken from the above Wikipedia article. Any live cell with fewer than 2 live neighbors dies as if caused by an underpopulation. Okay. Any live cell with 2 or 3 live neighbors lives to the next generation. Okay. Any live cell with more than 3 live neighbor dies as if by overpopulation. And any dead cell with exactly 3 neighbors, live neighbors, becomes a live cell as if by reproduction. The next state is created by applying the above rules simultaneously to every cell in the current state, where births and deaths occur simultaneously. Given the current state of the M by N grid board, return the next state. Okay, so here is that board. Okay, so it's M by N, right? Whatever, 3 by 4. Okay, only consists of 1s and 0s. And you can have a 2 by 2 board, whatever. You can have as little as 2 by 2, I guess, as to as big as the constraints say 1 to 25. Okay, so 25 square board would be humongous, right? So now the solution is to come up with the next state. So the first thing we think about is, we can do this the brute force way. Sometimes I go into the brute force way because it's educational to how this should work, and how the efficient way is. In this specific case, actually, the efficient way is really, really powerful. A really powerful method, I think, in state transition dynamics, and I will explain in a bit. But let's start with the simplest way possible. And remember, so here's the trick here in this Game of Life, or the thing to remember, is that this board state, right, as you update the cells, because you can imagine that you would be updating the values of these cells depending on values of surrounding cells, applying these rules. So I update this cell, update this cell with the values of these 3 cells, update this cell with the value of these 5 cells, update this cell with the value of these 3 cells, or as ascertained by rules that are specified and set in accordance with the values of these cells. In this case, and remember, I have boundaries here, so a neighbor in this case is all is all the cells around a given cell. So you can have up to 8 neighbors any one cell, and depending on whether it's on a boundary, if it's on a boundary, like one of these corners, it can have 3 neighbors. If it's at an edge of the matrix, it can have up to 5 neighbors, depending where on the edge it is, and yeah, so on and so forth. So let's take this and let's think about what we should do. So remember, we need these rules. Any live cell with fewer than 2 live neighbors dies as if caused by underpopulation. Okay, so the first thing we're gonna do, right? The first thing I'm gonna do is I'm going to, just to make this clear, and this is something I've been trying more recently, I'm going to define states, right? Int live equals 1. Okay, so so first we're gonna extract the board length to a variable, and n equals board of O dot length. Okay, we extract the board length to variable, so we don't have to spend a tiny bit of extra to extract that later, and it's easy to save on space. New board. Okay, so here let's start with what I'm gonna do here. We're going to have to go from one state to another state, and remember, in the state that we're in currently, we have to, every time we update this new state, for example 0 here, we need to take into account the zeros of the previous, or the values of the previous neighbors, right? So 0 here is because we have 1 live neighbor, and unfortunately if you have a dead neighbor, it's not going to come to life because of reproduction. It's going to stay dead, right? Okay, so that's still going to be 0, right? In this case, we have 1. So 1 is surrounded by 5 potential neighbors. One of them is alive only, and so that one that's alive is not enough to support this one, so that's 0. Again, similar reasoning 0 here. A similar reasoning. Now, for this next cell here, we move down 1 row. This next cell has 3 neighbors that are alive, right? So 1, 2, 3. Okay, so in the new matrix, we are going to switch that value over to 1, right? Because we're not going to do that in this matrix. And the reason why we're not going to do that in place here in this matrix is because using our current strategy, that will alter the next calculation, okay? Albeit in this particular case, it really won't. Actually, in this particular case, let's see. Live cells with 2 to 3 lives to the next generation. In this case, yes, it would do something, because if this was a 1 in the matrix itself for the next state, if I just in an isolated way look at this cell, it has 4 neighbors, right? So I guess it won't really do anything. But if you switch this cell over to 1, right, this guy would have 5 neighbors in the next calculation. But in truth, 5 neighbors who are alive. But in truth, this is he's only supposed to have 4 neighbors which are alive. Okay, so we have to distinguish that, because remember the rules: if you have more than 3 neighbors that are alive, then the cell will flip to dead. Okay, so we have to know that this new board state is going to be used, and we're going to copy states as we flip them over to the new board state. That's the general strategy. So for int I equals 0, I minus m, I plus plus, I'm just doing matrix iteration here. Okay, this shouldn't be too complicated, especially if you've done matrix problems before. For int j equals 0, j less than n, j plus plus. Okay, that's the secondary. Okay, now here's what I consider not exactly tricky, but you have to be careful with this part. Okay, so remember, when you're at a boundary, you're counting all the live neighbors, but at the boundary, if you go past the boundary, you can't calculate any more neighbors. Then if you try to go past the boundary, index into something else, you're going to get like an array out of bounds exception. So what we need to do, I've decided to break this down row by row, right? So if I is greater than 0 and j is greater than 0, if I is greater than 0 and j is greater than 0, what does that mean? That means the live neighbors plus equals board plus equals neighbors. And I'm going to have a live neighbors variable here. by the way, because each cell this is a loop, the inner loop where we're calculating the live neighbors, the so-called live neighbors. Okay, so the live neighbors equal 0. And so each cell moving forward, we're going to have, in this case, if the I is greater than 0 and j is greater than 0, right, that means we can just say that the live neighbors, I minus 1, board of I minus 1, j minus 1. Okay, now this may seem a little bit tedious because remember, we have to calculate all the live neighbors in the board. Okay, so that means we can go backwards one because that's important to know. If the next state, if I is greater than 0, live neighbors plus equal board I minus 1 j. Okay, now why am I doing this here? Why am I looking at only this condition on its own? Well, this means that if I is greater than 0, then we know that we can at least go back 1 to 0 if we're calculating the top row. Let's just put these as a top row calculation, and we can get all that. This element is still, there's going to be a row above whatever row we're at. Okay, in contrast, we'll have to do a condition check, set of condition checks for I equals 0, which means we can't go to the top row of the cell because we're already at the topmost row. Okay, that will cause an array out of bound indexing exception if we try. So anyway, let me finish up the top row. I greater than 0 and j less than -1. Okay, j less than, sorry, n minus 1. N minus 1 is the boundary up here that we calculated. Okay, just for reference. And live neighbors plus equals board I minus 1 j plus 1. Okay, we finished the top row. Okay, now again, I minus 1 because we still have a top row, j plus 1 because that means we're not at the edge, right? We're not at the rightmost column. That means we can go one to the right, and one of our neighbors is going to be at j minus 1, one of our neighbors is going to be at j, and one of our neighbors is going to be at j plus 1, and that goes for the top and bottom rows. So let's calculate the bottom row. Bottom row. So how does the bottom row work? So if I less than m minus 1 and j is greater than 0, live neighbors plus equal board I plus 1 j minus 1. Board is in board, not like bored, even though I did yawn. Okay, so again, why is this the case? Because we're at the bottommost row. This means we're not at the we still have a row that we can look ahead to. We're not at the bottommost row, okay? But we're looking at a row that's beyond the current row, right? So in m minus 1 is less than m minus 1, that means any of these two rows. If I was any of these two rows, then we can do calculations for the next row ahead, and this row can do calculations for this row, and so on and so forth, right? And j greater than 0 because we're not at the 0 edge, right? Very important, very important. Okay, next, if I is less than m minus 1, okay, remember, no j minus 1 because now we're not constrained by the being at that very edge of the board, right? Plus equals, very important, plus equals board I plus 1 j. Okay, you have to get some practice with these boundary conditions, right, in order to actually get them, because you know, a lot of this one is especially a little annoying, and you actually don't need to do all this boundary checking in this one. There's more efficient ways of doing that, but you know, they don't really increase decrease the code complexity. But as far as I'm concerned, this is more semantically readable. Neighbors plus equals board I plus 1 j plus 1. Okay. So again, so now we're here at the bottom row, and we're at the bottom row and the rightmost, and we're less than the rightmost edge. In this case, we're not necessarily less than the rightmost edge. Okay. So you got to think about this for a while if you're still not familiar. Same row. Okay. You got to think about this for a bit, because if j equals 0, this in an interview or something, this is the difference between passing and failing, obviously, in many cases. Plus equals board of I, j minus 1, and if j less than n minus 1, then in the same row, remember, we only have to check 2 elements. Why is that? I'll go into that in a second. As a reminder, neighbors, I should have just put live in. Neighbors plus equals board I j plus 1. Okay, and then now we've got all the rows, and we only need to check 2 rows in this case, because we don't need the item is not a neighbor of itself, right? So here's the kicker. If board I, this is where I'm implementing the rules. Okay, remember, there's those 3 rules that we need to implement when checking the board. And then okay, it's an if it's equal to dead, then we do something. What do? If live neighbors equals 3, then new board I j equals live. Okay, then so that corresponds to this condition. If we have if the cell is dead and there's 3 living neighbors, then it becomes a live cell as if by reproduction. And it doesn't regard, think about that, if by reproduction it becomes a live cell and other neighbors don't die, then there's going to be a crowding situation where someone's going to die, right? Anyway, 2, or next condition, neighbor is greater than 3. So board I j equals dead, otherwise new board I j equals live. Okay, so you might be asking what's going on here. I'm again just adhering by these rules here. Okay, anything's less than 2, live neighbors less than 2, it dies, or greater than 3, it's dead. And otherwise, we're just at the brink. We can set then the value of the neighbors for that element to live. Okay, now, since we're finally done with that inner loop, I feel that took a lot longer than if you were, crazy about coding. In this case, int I equals 0, I is less than m, I is less than m, I plus plus. Okay, and so this is where we copy the board. You might have asked why we're doing this. Well, I'm telling you, we need to copy, in this implementation, we need to copy this entire board over each time, because we're not overwriting cells in the same state. We have to do it in a new state. Okay, j plus plus, and finally board I j equals new board. new board, because that's what I defined that new board as, right? The placeholder for the original board after transition, and we don't have to return anything. Why? Because this is a void function, and this, looks at the memory space, obviously, of this void function behind the scenes. So let's go. Let's see what happens. Equals new board. Int new board equals new line 70 board equals we have to do I and J. You're not just setting the whole board equal. Okay. Accepted. Okay. And if we run it, bam, accepted. Okay. Now, that was one way of doing this. But is that really the most efficient way? No matter what Leetcode tells you, the answer is no. And the reason why is because we're doing an entire array copy at each iteration. Okay, what if we wanted to do this differently, where we didn't want to copy the array at each iteration? Now, this is where the trick comes in. Okay, if we wanted to do this in a more efficient way, dead to live, I'm going to show you a little trick, and this trick is crucial to problems like this. Okay, and the reason why is because right now we're not making optimal use of information. Okay, we have the ability to store multiple states, not just live and dead. Okay, in this case, what if we didn't have to just store live and dead? What if we could store dead to alive and live to dead as two states? Why would we do that? Now, the reason why is because I don't necessarily want to do a board copy each time. If I knew what the real state at any point was of an item after it's been checked, right, which requires imparting more information to the board, then I would not need to copy the board. I would just need to check the true correct state. Now here, what I'm doing, I'm determining whether a cell is alive, or rather should be alive, right, on the next transition, and is currently alive. So I should rename this as currently alive. So let's see, return 1, else return 0. Okay. Now this is whether the cell is alive, regardless of whether it's going to die in the next turn. And we know that it's going to die in the next turn because we have the rules which indicate that it's going to die in the next turn. We know that at least it's alive now, and therefore we can use it to calculate the next state on the same board, right? Okay, how do we get about to doing that? So first I wrote this CheckLive function because I want to essentially to tell whether it's going to get added to the neighbor count on the next iteration. We want to know if all its variations of live, whether it's alive now and for the foreseeable future, or where it's only alive now, only going to be alive for maybe another cycle, then we do this. We have to check live. So this is a lot of boilerplate, and I think I can reduce this code size, right? So, but either way, check live. I'm trying to use functional programming to make this clear. Check live. Oh boy, look how many check lives there are. I could probably check live. Okay, and a final check live for good measure. Check live. Okay. All right. So remember, check live returns what? Is 1 or 0. Okay. The true state upon the transition, because check live is essentially taking care of the final transition. Let this sink in a little bit, because this might need a little bit to sink in if you're not familiar with multi-state programming. But either way, so now we're no longer using that new board, so I'm getting rid of a reference to this, right? And this is where I'm interpreting what the board value should be changed to. So I j, okay, equals dead to live. Okay, what does that mean? And if live or dead. Okay, now this is the tricky part. Another tricky part, yay. So board of I of j equals board of ij equals live, or board of ij equals dead to live, then it's live or dead. So this is just telling the board for the new state whether it's currently alive. Okay, now this is important, and you'll see why. First, let's run this to see if this makes sense. Okay, run. Wrong answer. I must have missed something. Did I miss something? Did I miss something? I always miss something. Okay, let's do this. Live to dead. And dead to live. This is important to keep track of because wrong answer. Okay, let's see, what am I doing wrong here? Okay, I must have had some something wrong. Okay, my logic looks correctamundo. Board ij dead to live, live dead. Okay, it's got to be in these conditions here. This video is like super long. This is the longest video that I've done so far. I minus j, I'm okay, this is just checks. This should be the same as the previous function. I plus j, j minus I plus j. Okay, and let's just check my CheckLive function. Okay, and this looks, I think this is right. I don't need new board. That's one thing I can get rid of. So I'm getting rid of this new board. Okay. Okay. I is less than m. Let's try this again. Whoa. Whoa. Ah, ha 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 ha. This is the problem. That new board was throwing me off. I don't need that new board. Okay. That's very important. That's where you need to keep everything. And then we're accepted, and okay. So it doesn't look like the memory savings was a lot, but over the long run, that was accepted, and the memory savings is going to be like crazy. Okay, now this, what is the runtime of this? It's always going to be of O of m times n, right? Because you're going to have to go through every state, but the constant's going to be larger because with the new board it's going to be 2. So it's actually technically slower to do it with the second board because you're doing that extra copy over. But the second iteration is the space, right? And the space is going to be, in the first problem it's going to be O of n, but in the second solution it's going to be constant because we're not using extra space. We're not duplicating this board to do this operation. Okay, so great. Now that's the end of this. Phew. Okay, I'm glad we got through it. So yeah, if you like this video, if you found it informative, please like and subscribe. I have the code that I've written is on the link that I'm going to add to this. You can check that out, and you can see on my Leetcode profile what the deal is there. And yeah, that's it. So thank you. Appreciate you watching Coding with Chef, and I will see you next time. Remember, like, subscribe, comment on the link below, let me know what I'm doing wrong, right, etc., and I'll see you around.